Welcome to the next in our series, An Introduction to Mine to Mill. This presentation we're going to talk about blasting. Now I should point out this is very much an introduction to blasting, and it is very much for minerals processors rather than blasting engineers. Also, it's about open pit mining rather than underground mining. So let's look at some terminology associated with drill and blasting, and I've drawn this schematic based on the picture in the top right hand screen, which is a reproduction of that previous slide. And what we're seeing here is a bench, and you can think of a bench as being a ledge or a step. And over on our left here is our pit wall, and when we talk about bench height, it's this height here, and the bench height can vary depending on the size of the pit. There are other factors of course as well, but by and large the bigger the pit then the bigger the bench. And here is our floor. And basically what we want to do is to get the material inside that yellow boundary, drill, blast it, and get it to the comminution circuit. So we're going to drill lots of holes into the ground. So here are our blast holes, and they're going to be drilled down through and past where the new floor here is going to be. And that depth that the drill holes go beneath the floor is called subdrill. This orange part is where the explosive will be charged, so that's our explosive column. And right at the top, this volume here will be filled with material which is called stemming. When we look at this one blast hole here, this is the hole diameter. And this face over here we generally describe as being a free face. Now let's look at our bench in plan view. So we are now looking with the pit wall here. Here's our free face. And when we look at all our blast holes here, spacing is this dimension and burden is in this direction. And you will have heard miners talk about burden and spacing, and that's what they're referring to. Let's talk a bit about the terminology associated with the excavation phase once we've blasted our bench. Let's assume this material here is our blasted rock, and there are a number of ways that we can excavate it. One of those is simply to excavate in this direction across this entire face. Here we can see we are approximately halfway through excavating our bench. And here we have completed excavation. Another way is to divide our broken rock horizontally into layers or flitches. In this case, we are showing two flitches, a top one and a bottom one, but you can have as many flitches as you like. Each flitch is taken in turn, starting with the top one, and each flitch is excavated in this direction along this face. Here we can see the top flitch has been excavated, and the next phase will be for the bottom flitch to be progressively excavated. And when the bottom flitch has been removed, excavation is complete. Now, even though we're going to be looking at the comminution potential that drill and blasting gives us, we really do need to bear in mind the fact that blasting is not just about comminution. First and foremost, the ground has to be broken, and it has to be broken for a number of reasons. Firstly, you have to be able to dig it up, and we talk about diggability. It also needs to be easily fitted into a truck, because we use trucks mostly to transport the material from the mine through to the primary crusher. And then, of course, it has to be small enough to fit into the primary crusher. Now, once all those requirements have been satisfied, then we can start thinking about the comminution side of things, in that ideally we would like that distribution, broken fragments, to have a certain size to suit our comminution circuit. So when we look at the energy that our explosive provides us with, it needs to be able to give both shock, which is the energy that gives us fragmentation, and as comminutors that's what we are most interested in, but it also has to provide what we call heave energy, and heave loosens the broken rock and moves it to where it can be dug and loaded. And here we can see what is called the muck pile, which is our pile of broken rock after the explosion, and a ground engaging tool, in this case a bucket, in the process of digging it up. So let's have a look at the breakage zones in blasting. And here we can see near to the blast hole some intense size reduction breakage taking place. And here, further away from the blast hole, we are effectively liberating these blocks. We call these in situ blocks. And we can also see here heave taking place, where the explosive is transporting the broken material out onto the floor. These liberated blocks vary enormously in size. Here you can see how big some of these blocks can be, and they are a function of what we call structure. This would be considered as being highly structured, and you can see lots and lots and lots of small fractures and joints in this part of the face, and these, when they were liberated, would give us relatively small blocks. And this region here would be considered to have a medium structure, whereas this would be considered as massive. So let's see what happens during a blast, and I'm going to use this schematic with a single blast hole in our bench, and in this particular case the bench has a major joint just over here. In our drill hole, here is our explosive, and here is our stemming. So our explosive is detonated, and the first thing that happens is intense fracturing takes place in this brown zone here, where the local stress exceeds the rock strength. And at the same time, a compressive shock wave, that's the white dotted lines, starts to be propagated. The shock wave radiates further and further until eventually it meets this free face here. This is also a free face, and this joint also acts as a free face, and the compressive shock wave is reflected back. This time, however, it is a tensile wave that is reflected back. Now, breakage in tension requires a lot less energy than breakage in compression. So these tensile waves here are what we really are looking for to give us efficient breakage, and tensile waves are formed at any free face that the compressive wave meets. So free faces are very, very valuable. Meanwhile, adjacent to our blast hole, those initial fractures are now being invaded by hot expanding gases which the explosive has generated, and that gas penetration opens up those fractures further and further. Eventually, the combination of those hot expanding gases and the fracturing along fault lines and the structure we talked about before eventually bulges the free face out, and we see flexural rupture here and liberation of our in situ blocks. At the same time, if the stemming has not been done correctly, we will sometimes see the stemming being ejected out here. So now we know a little bit about what happens when blasting takes place. Let's have a look at how we can model fragmentation. A lot of work has been done in this area, and I'm not going to give you an exhaustive rundown of all the work that has been done. I've chosen three landmarks, I suppose one could call them, where significant advances were made, and we need to go back to 1973 for the first one, where a Russian man called Kuznetsov published this paper here, and he put together a model that took various blast information and predicted the mean fragment size from that information. 10 years later, Claude Cunningham, so in 1983, published this paper, and this was the first time we saw the name Kuz-Ram, and you'll hear that term Kuz-Ram quite a lot. The literature is full of descriptions of the Kuz-Ram model, and Claude Cunningham took Kuznetsov's equation and grafted on the Rosen-Ramler equation so that the entire distribution could be predicted. Now, that wasn't all he did with that work, but that was the main breakthrough that Cunningham made. He modified that initial model in 1983 and published a second paper in 1987, and they're both well worth looking at if you're interested in this area. 1983, let's go forward another 10 or 11 years to 1994, and Sharma Kanchibhotla, who was a student at the same time I was at the JKMRC, in fact I think he was in the office next to me, when he developed what we called the crushed zone model. And Sharma noticed, as a number of other researchers did, that the Kuz-Ram model, although it was very, very good, was effectively blind down at the fine end of the distribution. Now, the fine end of the distribution from a mining perspective is effectively our distribution from a Comminution viewpoint. It's where we are most interested in getting detail, and the Kuz-Ram model was not very good at providing that detail. And Sharma solved that fines inaccuracy problem. And 1994 was when he published his thesis. If you don't want to read all his thesis, and I would strongly recommend that you do, again, if you're interested in this area, a paper he published with Walter Valeri and myself, we give a very, very, very cut down version of Sharma's CZM model, crushed zone model. Let's have a quick look at the Kuz-Ram model. This first equation is Kuznetsov's equation. X is the mean fragment size, and that is predicted from this information here, which comes from the blast design plus some information about the rock. That's where this rock quality factor comes in. So K here is the powder factor, Q is the weight of explosive per hole, and E is the relative weight strength of the explosive. And over here we can see the Rosen-Ramler equation, and that picks up on this X term that Kuznetsov predicts and gives us the ability to predict the entire size distribution, providing that is you know this term N. And that was something else that Cunningham did. He developed some equations for estimating what M, the so-called uniformity exponent, should be from information mostly concerning the geometry of the blast. Now remember what I said, that the Kuz-Ram model was not very good at predicting fines. Fines in this case being defined in terms of mining, and anything below, I suppose, about 200, 300 millimeters from a mining perspective would be relatively fine. And we can see here the red dotted line, the Kuz-Ram prediction, predicts the measured ROM, which is the blue points there, very well indeed, down to about 300, maybe 250 millimeters. And afterwards it becomes progressively worse at estimating how much fine material there is in this particular run of mine. So let's see how well Sharma-Kanchibhotla's crushed zone model does. And you can see it matches the Kuz-Ram pretty well right the way down to around about 200, 300 millimeters. And then as we get finer, the crushed zone model follows the measured data very well indeed, and the Kuz-Ram model gets progressively worse and worse as we get finer and finer. So how does Sharma's crushed zone model work? Well, it describes this intense crushing zone here, which is where we believe a lot of the relatively fine material is generated, whilst at the same time recognizing that the Kuz-Ram model works really very well indeed for size reduction in this zone here. So schematically, the crushed zone model looks like this. If we consider just one explosive hole, which is here, and what his model does is estimate what this volume here is, which is where the intense breakage takes place. Not only does it estimate what that volume is, it also estimates what size reduction takes place within that volume, and he uses Comminution principles to do so. And that distribution is grafted onto a Kuz-Ram prediction, which is basically applied to this outer volume here, which we think all the coarser fragmentation takes place in. Now, the reason I've talked about modelling of fragmentation is that if you decide to embark on a mine-to-mill exercise and want to look at modifying blasting to help with comminution, the best way to do it, initially anyway, is to use modelling and simulation, because that gives you guidance as to the approaches which have the best chance of success, and it avoids costly and time-consuming trial and error in the field. The problem is, such simulations will only work if you've got a fragmentation model which is able to accurately predict the fine end of the distribution. A Kuz-Ram model won't do it. So whether you're going to develop your model in-house or get help from external consultants, you really do need to do your homework initially to make sure that the modeling capability that you are using is able to meet this requirement. At the same time, what you will be doing is passing those fragmentation model predictions onto a model of your ag and sag mill, and you have to make sure that that model can respond in a realistic way to whatever changes in the size distribution you've predicted from your fragmentation model. And that's why the JKMRC was so successful and able to mount those first mine-to-mill programs, because it had significant capabilities both on the fragmentation modelling side and on the ag and sag modelling side. So that's the end of our introduction to blasting, and the next and the last in this three-part series we'll be looking at how blasting can change ag, sag feed size to increase throughput.